Always you make me nervous, guys. Just first moment, I feel I need to say something. I think that's the reason hello is invented. Like you wanna fuck, what should I say? But like once the first minute passes, it's everything. First 5 seconds, right? First 5 seconds is very difficult. Categorification of Fourier theory. So what's up here now? What's up? I see. Wait a second. I know what's up. We didn't study game theory long time. We are going back to where we started, the playlist, and we are gonna keep watching. So we are at lecture 11, half through the course. Let's go watch it.
Welcome to CS229
No,
Machine
this
Learning.
one.
Hello everyone, welcome to CS229. Today we're going to talk about deep learning. And
Deep learning, guys, deep learning, finally. Neural networks, deep learning. Okay.
Hello everyone, welcome to
We started at a good position.
Today we're going to talk about deep learning and neural networks. We're going to have 2 lectures on that, one today and a little bit more of it on Monday. Don't hesitate to ask questions during the lecture. So stop me if you don't understand something and we'll try to...
Don't hesitate to ask questions, guys. If you don't understand something, it is your responsibility to ask questions.
Remembers logistic regression?
How are other people supposed to know that you have questions?
We're going to do that, explain how logistic regression can be interpreted as a neural network, specific case of a neural network, and then we will go to neural networks. Sounds good? So the quick intro on deep learning. So deep learning is a set of techniques that is, let's say, a subset of machine learning, and it's one of the growing techniques that have been used in the industry, specifically for problems in computer vision, natural language processing, and speech recognition. So you guys have a lot of different tools and plugins on your smartphones that uses this type of algorithm. Processing and speech recognition. So you guys have a subset of machine learning, and it's one of the growing techniques that have been used in the industry, specifically for problems in computer vision, natural language processing, and speech recognition. So you guys have a lot of different...
Speech recognition, NLP, and computer vision.
Tools and plugins on your smartphones that uses this type of algorithm.
How is that related to plugins?
The reason it came to work very well is primarily the new computational methods.
GPU.
So one thing we're going to see today is that deep learning is really, really computationally expensive, and people had to find techniques in order to parallelize the code.
Physics.
And use GPUs specifically in order to, graphical processing units, in order to be able to compute the computations in deep learning. The second part is the data available has been growing after the internet bubble, the digitalization of the world. So now people have access to large amounts of data. And this type of algorithm has the specificity of being able to learn a lot when there's a lot of data. So these models are very flexible, and the more you give them data, the more they will be able to understand the salient feature of
deep learning. And it's actually related to my thesis too. Good. One reason, it was actually Monzer's presentation too. Monzer is publishing a book. Actually, I think he was going to publish it May 1st, right? End of April. well, I don't know, publish, but he will be done with it, something like that. What that stage is called, I don't know. And one of the things that changed everything in engineering and social science is that we can do machine learning, and now we have a lot of data. Also, I'm interested to find if MIT OpenCourseWare open. What are the lists? Explore. Calculus. Okay. Department, computer science. That's a good course. Programming in Java or not. These are sciences that nobody uses anymore, by the way. Advanced not advanced, just the algorithms. Programming languages may be something good I want to learn. I want to see if they have a machine learning course. Introduction to algorithm. That's a good course. I want to learn this one. Introduction to machine learning. These two are good. Let me add them here. Because I registered for a course, but I didn't attend because of my injury. So I don't think I have the time also to just go to the classes. So after finishing the ML Andrew NG, start MIT OCW Introduction to Algorithm. Yeah, we want to have just a beginner level understanding. Actually, I don't want to have an advanced understanding unless it is needed in my profession. Introduction to machine learning. What else do they have? Maybe design and analysis of algorithms. And let's get the course 6.0 towards it. When we make time. Is there any other course that can help us for getting interviews done? Like advanced stuff, I don't want to learn them, to be honest. Like, if you have no motivation, my motivation is my internship, right? If it was up to me, I wouldn't study any of them. It is not something I like. But I like getting past the interview. So as long as my motivation, I have that can be a nice course, which I could have taken, but I didn't. Do we have the videos? Oh, learning in games. That's a good course that we know it exists. Let's add this note somewhere else. Maybe for my thesis I can use it. Game theory with engineering application. And hopefully we can make it applied, make my thesis applied. Actually, I can ask also too, if they know from people from Amazon. I can reach out. Well, introduction to algorithm, we had it. Oh, probabilistic systems analysis and applied probability by Munzer. How many introduction to algorithms? Mathematics for computer science. Again. Introduction to deep learning. Alexander Amini. Yes. They have a course machine learning. They're actually this order actually, this maybe. Again, I should add a maybe here. Street fighting. What? Street fighting mathematics. I think we found what we found. We just want to now have more problems so that overwhelm ourselves. Fuck that. Don't look more. Yeah, first two courses were enough for us. Introduction to algorithm and introduction to machine learning. These are not necessary at all. The rest. Do not overwhelm. There are a lot of things in this world. There are too many information. We don't need all of them. Actually, we need as least as possible information. Keep it super simple. Not necessary right now. At all. For me, it is that I want to learn more, read more, because I want to take less action. That's what it is. When you need it, go read it. Woo! When you need it, go read it. You don't need it, don't make artificial need for yourself.
And finally, algorithms. So people have come up with new techniques in order to use the data, use the computation power, and build models. So we're going to touch a little bit on all of that. But let's go with logistic regression first. Can you guys see in the back? Yeah? Okay, perfect. So, you remember what logistic regression is? We're going to fix a goal for us that is a classification goal. So let's try to find cats in images. So find cats in images. Meaning binary classification. If there is a cat in the image, we want to output a number that is close to 1, presence of a cat. And if there is no cat in the image, we want to output 0. Let's say for now we're constrained to the fact that there is maximum 1 cat per image. There's no more. If you had to draw the logistic regression model, that's what you would do. You would take a cat. So this is an image of a cat. Very bad at that.
So wait a second. This guy puts his content on.
So much more.
How to get the most of Grammarly free.
It's Kayla on behalf of Grammarly to tell
Pervasive than it has ever been before in our lifetimes. It's right. So for any instantiation of our weights, we can compute a scale.
What is the same thing?
Dense layer. Right? I'm just reciting a chain rule here from calculus. This is possible because y is only dependent on the previous layer. And now let's suppose we don't want to do this for W2, but we want to do it for W1. We can use the exact same process, right? But now it's one step.
There is one that is 2 days ago, and there is one which is 1 year. They're the same? No, they're very different.
Multiplied by dy dw2, right? This is all possible, right? It's a chain rule. I'm just reciting a chain rule here from calculus. This is possible because y is only dependent on the previous layer. And now let's suppose we don't want to do this for W2, but we want to do it for W1. We can use the exact same process, right? But now
Good to know that these courses exist. So once we need them, we can go look at them. You know? Great. Now we are good. Now we have to. This is our mission.
Sorry. In computer science, you know that images can be represented as 3D matrices. So if I tell you that this is a color image of size 64 by 64, how many numbers do I have to represent those pixels?
120.
Yeah, I heard it. 64 by 64 by 3. 3 for the RGB channel.
But each one
Red,
of them has intensity, right?
Green, blue. Every pixel in an image can be represented by 3 numbers, one representing the red filter, the green filter, and the blue filter. So actually, this image is of size 64 times 64 times 3. Does that make sense? So the first thing we will do in order to use logistic regression to find if there is a cat on this image, we're going to flatten this into a vector. So I'm going to take all the numbers in this matrix and flatten them in a vector. Just an image to vector operation, nothing more. And now I can use my logistic regression because I have a vector input. So I'm going to
I'm getting distracted. Okay,
to take
let's
all
keep
of these
connected to this.
and push them in an operation that we call usually the logistic operation, which has one part
Logistic operation.
wx plus b,
Wx plus b.
is going to be the image. So wx plus b. And the second part
So
is
x
going
is
to
the
be the
image, and we have wx plus b.
Everybody's familiar with the sigmoid function? Function that takes a number between minus infinity and plus infinity, maps it between 0 and 1. It's very convenient for classification problems. And this we're going to call it y hat, which is sigmoid of what you've seen in class previously. I think it's theta transpose x. But here we will just separate the notation into w and b. So can someone tell me what's the shape of w?
What do you mean?
Matrix w.
What does he mean when he says shape of w? Shape of w. So x. Oh, okay. Yes. X is a 64 by 64 matrix, and times 3. W. So it's like 64, 64 times 3, 1 times this vector.
Vector matrix.
B is a number, right?
Hmm?
Yeah, so that.
What? Yeah, 64 by 64 by 3 as a, yeah. So you know that this guy here is a vector of 64 by 64 by 3, a column vector. So the shape of x is going to be 64 by 64 by 3 times 1. This is the shape. And this, I think it's that, if I don't know, 12,288. And this, indeed, because we want y hat to be 1 by 1, this w has to be 1 by 12,288. Does that make sense? So we have a row vector as our parameter. We're just changing the notations of the logistic regression that you guys have seen. And so once we have this model, we need to train it, as you know. And the process of training is that first we will initialize our parameters. These are what we call parameters. We will use the specific vocabulary of weights and bias.
Bias, B is bias.
I believe you
offset.
guys have heard this vocabulary before, weights and biases. So we're going to find the right W and the right B in order to be able to use this model properly. Once we initialize them, what we will do is that we will optimize them. Find the optimal W and B. And after we found the optimal W and B, we will use them to predict. Does this process make sense, this training process? And I think the important part is to understand what this is. Find the optimal W and B means defining a loss function, which is the objective. And in machine learning, you often have this specific problem where you have a function that you know you want to find, the network function, but you don't know the values of its parameters. And in order to find them, you're going to use a proxy that is going to be your loss function. If you manage to minimize the loss function, you will find the right parameters. So you define a loss function that is the logistic loss, y log of y hat plus 1 minus y log of 1 minus y hat, up. You guys have seen this one. You remember where it comes from? It comes from a
Y log Y, this is information theory.
maximum likelihood
Makes sense.
estimation,
Okay.
starting from a probabilistic model. And so the idea is, how can I minimize this
Log
function?
likelihood.
Minimize because I've put a minus sign here. I want to find W and B that minimize this function, and I'm going to use a gradient descent algorithm, which means I'm going to iteratively compute the derivative of the loss with respect to my parameters. And at every step, I will update them to make this loss function go a little down at every iterative step. So in terms of implementation, this is a for loop. You will loop over a certain number of iterations,
Oh, okay.
and at every point, you will compute the
We
derivative
have
of your loss
these
with respect
in
to
like
your parameters.
numerical methods. In
Everybody remembers how
undergrad.
to compute this number? Take the derivative here. You use the fact that the sigmoid function has a derivative that is sigmoid times 1 minus sigmoid, and you will compute the result. We're going to do some derivative later today, but just to set up the problem here. So the few things that I want to touch on here is, first, how many parameters does this model have, this logistic regression?
W and B, right? They are the only ones. So 1, 20, 29, 8, 9.
If you have to count them.
This guy looks like a smart guy. I don't know why, but
So this is the number, 89, yeah, correct.
Ah.
So 12,288 weights and 1 bias. Does that make sense? So actually it's funny because you
Like,
can
he's
quickly
very
count it by
confident
just
when he's
counting the number
teaching.
of edges on the
is he a
drawing.
teacher? Who
plus
are
1.
they? They are TAs, right?
Every circle has a bias. Every edge has a weight.
I
Because
would be
ultimately,
super nervous
this operation,
talking in front of a
you
class.
can rewrite it like that, right? It means every weight has every weight corresponds to an edge. So that's another way to count it. We're going to use it a little further. So we're starting with not too many parameters, actually. And one thing that we notice is that the number of parameters of a model depends on the size of the input. We probably don't want that at some point. So we're going to change it later. So 2 equations that I want you to remember is, the first one is neuron equals linear plus activation. So this is the vocabulary we will use in neural networks. We define a neuron as an operation that has 2 parts, one linear part and one activation part. And it's exactly that. This is actually a neuron. We have a linear part, Wx plus b, and then we take the output of this linear part and we put it in an activation that in this case is the sigmoid function. It can be other functions. Okay? So this is the first equation. Not too hard. The second equation that I want to set now is the model equals architecture plus parameters. What does that mean? It means here we're
So neuron means a linear and then sigmoid on it, activation. Model means architecture plus parameters. Architecture is linear, for example, or sigma. The neuron, right, is architecture. Parameter, or maybe also the objective function. Parameters are the W and B.
We're trying to train a logistic regression. In order to be able to use it, we need an architecture, which is the following, a one neural network, and the parameters, W and B. So basically, when people say we've shipped a model, like in the industry, what they're saying is that they found the right parameters with the right architecture. They have 2 files, and these 2 files are predicting a bunch of things. Okay? 1 parameter file and 1 architecture file. The architecture will be modified a lot today. We will add neurons all over. And the parameters will always be called W and B, but they will become bigger and bigger. Because we have more data, we want to be able to understand it. You can get that it's going to be hard to understand what a cat is with only that many parameters. We want to have more parameters. Any questions so far? So this was just to set up the problem with logistic regression. Let's try to set a new goal after the first goal we have set prior to that. So the second goal would be find cat, lion, iguana in images. So a little different than before. Only thing we changed is that we want to now to detect 3 types of animals. If there's a cat on the image, I want to know there's a cat. If there's an iguana on the image, I want to know there's an iguana. If there's a lion on the image, I want to know it as well. So how would you modify the network that we previously had in order to take this into account?
Find cat, lion, and iguana in image. You come with another W and B for iguana and lion.
Yeah. Yeah, good idea. So put 2 more circles, so neurons, and do the same thing.
Neurons. Yeah.
So we have our picture here with the cat. So the cat is going to the right. 64 by 64 by 3. We flatten it from x1 to xn. Let's say n represents 64, 64 by 3. And what I will do is that I will use 3 neurons that are all computing the same thing. They're all connected to all these inputs. Okay? I connect all my inputs, x1 to xn, to each of these neurons. And I will use a specific set of notation here. Okay. y2 hat equals a21 sigmoid of w21 plus x plus b.
Don't look at your phone.
And similarly,
Don't look
y3
at your
hat
phone.
equals a31, which is sigmoid of w31 x plus b31. So I'm introducing a few notations here, and
So he keeps the sigma the same. He doesn't change like sigma 1, sigma 2.
we'll get used to it, don't worry. So just write this down and we're going to go over it. So the square brackets here represent what we will call later on a layer. If you look at this network, it looks like there is one layer here. There's one layer in which neurons don't communicate with each other. We could add up to it, and we will do it later on. More neurons in other layers. We will denote with square brackets the index of the layer. The index that is the subscript to this A is the number identifying the neuron inside the layer. So here we have one layer. We have A1, A2, and A3 with square brackets 1 to identify the layer. Does that make sense? And then we have our y hat that instead of being a single number as it was before, is now a vector of size 3. So how many parameters does this network have?
Times 3. The same shit times 3.
How much? Okay, how did you come up with that? Okay, yeah, correct. So we just have 3 times the thing we had before because we added 2 more neurons and they all have their own set of parameters. Look, like this edge is a separate edge.
If you didn't change
so we have to
sigma.
replicate parameters for each of these. So W11 would be the equivalent of what we had for the cat, but we have to add 2 more
Oh my god.
parameter
Shout out
vectors
to
and biases.
StrengthSide for
So
this.
other question. When you had to train this logistic regression, what data set did you need?
Logistic regression.
Can someone?
For logistic regression, what do we do? It's another linear function, right? Ax plus b. So, same thing.
Try to describe the data set. Yeah. Yeah, correct. So we need images and labels with it, labeled as cat 1 or no cat 0. So it's a binary classification with images and labels. Now, what do you think should be the data set to train this network?
Oh my god.
Yes, go for it.
What was the other one? That's a good teacher, by the way. No? First of all, if you are a student, it's your responsibility. If you don't understand the part, you ask question. Don't be worried that you look stupid because other people are stupid like you. All of us are stupid. You are just a stupid person who asks question. Then, something that I never did. Like when I was in classroom, a lot of times we didn't ask question. And another guy asked question. I was, oh, thanks God somebody asked. And if you don't ask question, you lose the track. Anyways, I won't take any classes, but if any one of you wants to take classes, know that. But he's a good teacher because he makes sure students are understanding the situation.
That's a good idea. So
Doesn't assume
just
that,
to
oh,
repeat,
everything is simple.
A label for an image that
Yeah, I
has a
like
cat
his pace. Like he's
would
not going
probably
very
be
fast.
a vector with a 1 and 2 zeros, where the 1 should represent the presence of a cat. This one should
I like
represent
his
the
pace.
presence of a lion, and this one should represent the presence of an iguana. So let's assume I use this scheme to label my data set. I train this network using the same techniques here. initialize all my weights and biases with a value, a starting value, optimize a loss function by using gradient descent, and then use y hat equals blah, blah, blah to predict. What do you think this neuron is going to be responsible for? If you had to describe the responsibility of this neuron. Yes. Well, this one. Yeah, lion, and this one iguana. So basically, the way yeah, go for it. That's a good question. We're going to talk about that now. Multiple images contain different animals or not. So going back on what you said, because we decided to label our data set like that, after training, this neuron is naturally going to be there to detect cats. If we had changed the labeling scheme, and I said that the second entry would correspond to the cat, the presence of a cat, then after training, you will detect that this neuron is responsible for detecting a cat. So the network is going to evolve depending on the way you label your data set. Now, do you think that this network can still be robust to different animals in the same picture? So this cat now has a friend that is a lion. Okay, I have no idea how to draw a lion, but let's say there is a lion here. And because there is a lion, I will add a 1 here. Do you think this network is robust to this type of labeling?
No. Yes. Yes, I say it is robust.
It should be. The neurons aren't talking to each other. That's a good answer, actually. Another answer?
I say yes because we need to be positive.
It should be. The neurons aren't talking to each other. That's a good answer, actually. Another answer? That's a good intuition, because the network, what it sees is just 1, 1, 0 and an image. It doesn't see that this one corresponds to, the cat corresponds to the first one, and the second, and the lion corresponds to the second one. So this is a property of neural networks. It's the fact that you don't need to tell them everything. If you have enough data, they're going to figure it out. So because you will have also cats...
That's the whole idea behind machine learning. We have data, we have the function. Don't make it complicated.
With iguanas, cats alone,
give the
lions
data,
with iguanas,
give what
lions
you want.
alone. Ultimately,
the rest is
this
on
neuron will
data
understand
science.
what it's looking for. And it will understand that this one corresponds to this.
We need to have a toolbox machine learning, which we
just
have.
needs a lot of data.
And the rest
so
is
yes,
not
it's going to be
our
robust,
thing.
and that's the reason
Somebody else
mentioned.
designs
It's going to be
it.
robust
That's called
that
machine
because
learning
the three
engineer
neurons
or
aren't
what.
communicating together. So we can totally train them independently from each other. And in fact, the sigmoid here doesn't depend on the sigmoid here and doesn't depend on the sigmoid here. It means we can have 1, 1, and 1 as an output. Yes, question. You could think about it as 3 logistic regressions. So we wouldn't call that a neural network yet. It's not ready yet. But it's a 3 neural network or 3 logistic regression with each other. Now, following up on that. Yeah, go for it, question. W and B are related to what? Oh, yeah. So usually you would have theta transpose x, which is sum of theta I xi, correct? And what I will split it is, I will split it in sum of theta I xi plus theta 0 times 1. I'll split it like that. Theta 0 would correspond to B, and these theta i's would correspond to wi's. Make sense? Okay. One more question, and then we move on. Good question. That's the next thing we're going to see.
This is a good fucking
the question
teacher.
is
He's
a
a good
follow-up on
fucking
this.
teacher.
Is there cases where we have a constraint
Let's
where there is
assume-
only one possible
ask,
outcome.
and he's not
It means
in rush.
there is no cat and lion. There's either a
But the
cat
thing is
or a
that
lion.
the course takes
There's no
forever,
iguana
probably.
and lion. There's
But
either
people
an
are
iguana or a lion.
understanding, and he encourages.
Think about healthcare. There are many models that are made to detect if a disease, skin disease, is present based on cell microscopic images. Usually, there is no overlap between diseases. It means you want to classify a specific disease among a large number of diseases. So this model would still work, but would not be optimal because it's longer to train. Maybe one disease is super, super rare, and one of the neurons is never going to be trained. Let's say you're working in a zoo where there is only one iguana, and there are thousands of lions and thousands of cats.
That shows he's a mental masturbator. He doesn't know in zoos we don't have thousands of lions. I don't know how many lions do we have in the world. Cat, we can have a lot. Cat, for sure, we have millions. But lions, population. I say, fuck, 1 million? 1 million is too much. I say even we don't have 100,000. Population of lions in the world. 20,000 and 25,000. Motherfucker, it says 1,000. There is a zoo that there's 1,000 lions. Cats. How much cats? I said not even 100,000. For cats, we are 8 billion people. I say above 500 million. No, dude, that's too much. 100 million, above 100 million. Around 600 million. Wow, cats and lions, that's the
This
difference.
guy will never train, almost. You know, it will be super hard to train this one. So you want to start with another model where you put the constraint that, okay, there's only one disease that we want to predict. And let the model learn, with all the neurons learn together by
Good
creating
estimations, by the way.
interaction.
Good job, me. Good job, me.
Have you guys heard of Softmax? Yes, some of you, I see that. Okay. So let's look at Softmax a little bit together. So we set a new goal now, which is we add a constraint which is unique animal on an image.
Softmax, what is
So at most one animal on an image. So I'm going to modify the network a little bit. We have our cat and there is no lion on the image. We flatten it. And now I'm going to use the same scheme with the 3 neurons. A1, A2, A3. But as an output, what I'm going to use is an exponent, a softmax function. So
Dude,
let
don't
me
get
be more precise.
distracted.
Let me
Keep in touch, right? Talk, say cat. Repeat after him. Whatever.
actually introduce
Softmax.
another notation to make it
Don't
easier.
get distracted.
As you know, the neuron is a linear part plus an activation. So we're going to introduce
Neuron and
a notation
oh,
for the linear
and
part.
activation. Neuron
I'm going
is
to
linear.
introduce Z11 to represent the linear part of the first neuron.
Just introducing new terms for
Z1.
bullshit. Alright.
1, 2,
Alright.
to introduce the linear part of the second neuron. So
Alright.
now the neuron has 2 parts,
All
one
right.
which computes Z and one which computes A
Nuance.
equals C.
Linear.
Now,
activation,
remove all the activations
softmax, cats,
and make these
iguana, lions, estimation,
and I'm
neural
going to use a
networks.
specific formula. So this, if you recall, it's exactly the softmax formula.
So softmax is e to the z over summation of e to the z, 1 to 3. Why do we want that? So we have iguana, lion, and is it the activation? Oh, softmax is our okay. Softmax, yes, softmax is our activation, is the sigmoid function, and we have 3 different of them: e to the lion over sum of the lion and cat and iguana. Now these 3 softmaxes relate to each other. Or they don't. They do relate.
Yeah. Okay, so now the network we have, can you guys see or it's too small? Too small? Okay, I'm going to
Fucking
just
teacher, he's the
write this
best
formula
teacher
bigger,
ever.
and then you can
Asking
figure out the others, I
everything.
guess.
Oh, I loved
E
it.
of Z3
He just
1
zooming out.
divided by sum from k equals 1 to 3
He's really
of
nice.
E exponential of zk.
It was a long time ago.
This
I
one?
haven't watched this series.
So here is for
But
the third one. If you were doing it for the
This
first
guy
one, you will
is so
add.
patient.
You just change this into a 2, into a 1. And for
Well,
the second
you
one,
may
into a
say,
2.
okay, he doesn't teach a lot of subject, but at least the part he teaches, people can learn. I don't know what
So
is
why
the
is this formula
perfect
interesting,
ratio.
and why is it not
But
robust
I think
to
this kind of teacher are missed a lot.
labeling scheme anymore? Is because the sum of the outputs of this network have to sum up to 1. You can try it. If you sum the 3 outputs, you get the same thing in the numerator and on the denominator, and you get 1. Does that make sense? So instead of getting a probabilistic output for each of y, if each of y hat 1, y hat 2, y hat 3, we will get a probability distribution over all the classes. So it means we cannot get 0.7, 0.6, 0.1, telling us roughly that there is probably a cat and a lion but no iguana. We have to sum these to 1. So it means if there is no cat and no lion,
They are
it means there
related.
is very likely an iguana. The 3 probabilities are dependent on each other.
Yes, this is not the case. Like
And for this one, we have to label the following way. 110 for a cat, 010 for a lion, or 001 for an iguana. So this is called a softmax multi-class network. You assume there is at least one of the 3 classes, otherwise you have to add a 4th input that will represent an absence of animal. But this way, yeah, you assume there's always one of these 3 animals on every picture.
don't look at your
How many
phone.
parameters does the network have? The same as the second one. We still have 3 neurons, and although I didn't write it, this Z1 is equal to W11 X plus B1, Z2 same, Z3 same. So there's 3n plus 3 parameters. So one question that we didn't talk about is how do we train these
5
parameters?
more minutes. Actually,
These
timers are
parameters,
defined for
the 3n
this.
plus 3 parameters, how do
Set
we train them?
timer.
You think this
You,
scheme will
you
work or
don't
not?
think about
What's
time
wrong-
anymore.
what's wrong with
it
this
tells
scheme?
you 1 hour after. So your focus is all about this.
What's wrong with the loss function specifically?
That is the goal of time. The goal of
There's only two outcomes.
clock,
So
the goal of
in this loss function,
watch, the goal of
y
your
is a
phone
number between 0 and 1.
timer is
Y hat
that to let
same is a
you
probability.
forget
Y is either
about
0
the
or
time.
1. Y hat is between 0
They
and 1.
are
So it cannot
taking control
match
of it and they will
this
let you
labeling.
know.
So we need to modify the loss function.
Not that we look at phone now, what time is it now?
So
How
let's
long
call
is
it
left? No, that is not
Loss
the
3 neuron.
goal they are designed for. The goal of a timer
What I'm
is
going to do
let
is I'm
you
going to
not
just
think about the
sum
time.
it up for the 3 neurons.
Fuck time, fuck minutes, fuck seconds, fuck hours, fuck days. Just like this guy, be patient. We have every time in this life. What is the point of rushing?
Does this make sense? So I'm just doing 3 times this loss for each of the neurons. So we have exactly 3 times this. We sum them together. And if you train this loss function, you should be able to train the 3 neurons that you have. And again, talking about scarcity of one of the classes. If there is not many iguana, then the third term of this sum is not going to help this neuron train towards detecting an iguana. It's going to push it to detect no iguana. Any question on the loss function? Does this one make sense? Yeah. Yeah, usually that's what will happen is that the output of this network, once it's trained, is going to be a probability distribution. You will pick the maximum of those and you will set it to 1 and the others to 0 as your prediction. One more question, yeah.
Contempt for time.
If you use the 2-1, if you use this labeling scheme, like 1-1-0 for this network, what do you think will happen?
That's an interesting question. 1-1-0, they are related to each other. So, what does 1-1-0 mean? What is the odds that we can find a cat and a lion together? So because they should sum to 1. Once we add cat, we are decreasing lion.
It will probably not work. And the reason is this sum is equal to 2, the sum of these entries, while the sum of these entries is equal to 1.
Yeah.
So you will never be able to match the output to the input, to the label. Does it make sense? So what the network is probably going to do is it's probably going to send this one to 1/2, this one to 1/2, and this one to 0, probably, which is not what you want. Okay.
I get it.
Let's talk about the loss function for this softmax regression.
Okay guys, I think we are good for today. The rest for tomorrow. It's a good subject. Stop recording. I'm gonna stop, but we are going to stop because we wanna start again. Not we wanna stop forever.